like this. And what we've got is, so the equation you've got is you've got your heat equation. It's going to be again, the partial of U with respect to T is equal to some K0 second partial of U with respect to X squared. And does this one have a plus a Q? I don't think so. Oh yeah, it does have a Q. So yeah, so then you have plus a Q. All right, and you basically have two differential equations in this form, right? And what you've got is you've got a boundary condition. So let me go ahead and say that we have a 1, a 1, a 1, and a 1, and we have a partial of U2 with respect to T of K20 second partial of U2 with respect to X squared plus a Q2. You look at those particular ones. Then, if I remember correctly, this was non-zero and this one was 0, so this was 0 here. You get two different values there. And we know that we're looking at equilibrium, so we have the partial of U1 with respect to T is equal to the partial of U2 with respect to T is equal to 0, right? So then what we're going to get here is you're going to have a U1 equilibrium double prime is equal to minus Q1 over K10, and you're going to have a U2 equilibrium double prime is equal to, in this case, is going to be equal to 0, right? Those are going to be because the Q2, I think everybody had Q2 equals 0, is that correct? Okay, so the Q2 is equal to 0. All right, so this particular one, of course, we can solve. These ODEs everybody can solve, right? These should be easy to solve, these ODEs. In particular, of course, E1 equilibrium of X is going to be equal to minus Q1 X squared over K2 K1 0. And then you're going to get plus a C1X plus a C2, right? And you're going to have the equilibrium there. That's just going to be a linear function. Second derivative is equal to 0. So this one has to be they're new constants, d1x plus a d2 there. All right? And then we have conditions. So one of the easy ones is, so we had homogeneous boundary conditions. We had that U1 of 0 was equal to 0. What does that tell us? Right away.
C2 equals to 0.
That tells us that C2 equals 0. We also have that U2 at 2, or was it always? Yeah, it's always at 2. This was like the 2 bar, I think, was equal to 0. All right, that gives us a relationship right here. This one's going to imply what? Well, if at 2 this is equal to 0, then that tells us that 2d1 plus d2 equals 0. So we could say, for example, d2 is going to be equal to a minus 2d1. All right. So now, again, what we have we have 4 arbitrary integration constants from our 2 differential equations for these 2 bars. Think of them as it's a single bar, but they're connected, right? But then we have to have what we have to have is we have to have that U1 equilibrium at 1 must equal U2 equilibrium at 1. All right? We have to have that particular condition saying that where these two bars join together, their temperatures are the same. The other condition tells us what? It tells us that the flow at that boundary. So it's basically, let me see if I have this correct. We should be having that the K10 U prime 1 equilibrium at 1 must equal the K20 U2 equilibrium prime at 1. In other words, we're saying that the heat flowing through that junction between the two bars must also match. Temperatures match and the flow matches. The flow of heat. You don't have a misbalance of heat flowing across that junction. So these are two more algebraic expressions, right? With those two more algebraic expressions, we should then be able to solve for the other two constants. Basically, we had four conditions, right? The two end boundary conditions, and then we have the matching condition of the temperature and the flux condition of the two ones. So we've now got four conditions with four unknowns, right? And so you're just solving four linear equations and four unknowns. But some of them are easy. It's not as if this is a full spectrum matrix to solve. And so that's how you solve this particular one. I'm not supposed to click on it.
So just to make sure, so the notation in the problem of K naught and in parentheses 1 minus and K naught parentheses 1 plus, that just means the K naught that's with respect to the
each
left
of the bars.
side. Okay.
Yeah, it's purely saying look at the conditions between the two at the two bars. Clicked on that and I'm getting nothing again. I hope they do send something. All right. Does that help on the problem 4? Okay. Again, so all of these problems really are reducing back to, well, we extended our 237, 337 problems, ODE problems. The equilibrium makes some ODE problems, and we're now changing, instead of initial value problems, into boundary value problems. That's the only difference here. As I mentioned last time, and it also relates to the lecture activity 2 problem, it's going to be very important that we find the equilibrium solution. Because if we're going to solve it, I think everybody agrees, if we're going to be doing a superposition principle, you add solutions together. If you don't have zeros on the boundaries and you add them together, you're not going to get a solution. You have to have homogeneous boundary conditions, and you also have to have a homogeneous differential equation, right? If it's not a homogeneous differential equation, the differential equation doesn't satisfy adding two together. A U1 plus a U2, if the differential equation is non-homogeneous, you don't have superposition there. Okay? So we need to be able to do that. Okay. So that's why we need to solve these. We need to solve these equilibrium solutions first. And we're soon going to have, I'm going to be able to project the slides. We're soon going to have conditions that we can, will show when we can have solvability.
Were you having issues with your PC?
Doesn't work at all.
Yeah.
Anything you can do would be nice so I can lecture. So just waving hands at everybody. I was told that this thing was failing a lot last semester, and that it's just, it's, I think something's fundamentally wrong with the PC. We know they're junkers who got them from the 1980s. Oh, it's coming on, yay. Okay. So that's the key to these problems, is we first gotta get these ODEs taken care of so we can subtract them out to get the homogeneous one, so we can do the other ones. All right, good. What was the secret that you did, by the way? What secret did you do so that I can do it in the future, maybe?
So you just restarted?
I'll just press the button.
I did that like a dozen times.
I'll make a service ticket.
Yeah, I tried and tried and tried, I guess. You just have the secret magic touch.
Hold on.
All right, thanks. Oops. Okay, so now we can actually access problems here. By the way, you can see I've got the solutions up to the lecture activity there. I'll soon put the solutions to the textbook one soon. Probably tomorrow. And I'm almost halfway graded through the textbook. Okay. Any other questions on the web work problems? Yes.
For 5, because it's non-homogeneous, I wasn't sure how to approach it. I kind of want to do a full separation of variables derivation from scratch, also since it's Neumann boundary conditions, but
You don't really want to do that.
okay.
Okay, so we're looking at 5. So again, when you're looking at the answer down here, we're looking for what? The equilibrium answer, right? So the equilibrium answer says we're just looking at the ODE problem here.
Is that valid even if you're trying to find the values of beta that solve the better solutions to the whole heat equation, not just the equilibrium?
So one of the important things, the assumption is that the partial v with respect to t is equal to 0. And so equilibrium means there is no change in time.
Yeah, okay, and that's
so that-
also true for the
that's
first part of the
in-
problem? Or
Well,
that's also what they're
that's
asking?
in a whole part in here.
Oh, okay.
So what is happening in this particular one? In this one, we can see that all along the bar, there's heat being generated, right? We have flux coming in from the left-hand side, heat generated all along the bar, and then flux going out the right-hand side. And what must be true if that's equilibrium? If it's equilibrium, what's being generated in the bar, what's coming in better equal what's going out. Or else you aren't in equilibrium, right? Because as time would pass along, if you're generating more heat or having more coming in than's going out, the bar would keep rising in temperature. That violates partial of u with respect to t equaling 0. Okay? Equilibrium really is what you think equilibrium is. It stays at some equilibrium value, some constant.
Is it as simple as the flux plus the Q?
The flux plus the Q, no, that's generated per unit length. So here I have a length 3, so it's generating that 3 units, 3 of those units, right? That was in, because when we did this, we did the little delta X's and stuff.
Mhm.
And so those are always generated per length. So if we have something greater than 1, then we're going to have to integrate over the length 3. Of course, constant integrated over 3 is not a hard problem. Okay? Does that make sense to people? If we're gonna get that balance in energy, that's what has to happen. And so then the first thing is getting the beta, then it reduces to some of the problems you were doing before, and you're matching things up. Okay? And again, it's just equilibrium stuff. And then what's true about it, initially we have this exponentially damped part, and over time, what's gonna happen to that initial distribution of heat? It's gonna spread out, isn't it? It's gonna all flatten out. It's not gonna actually flatten out because you have this generated all along the way. So we have this part contributing, giving a quadratic expansion of stuff there. But then you'll have to, this part, so then you can get the integration constant has to be the average of what was initially in that bar. So, and of course, you love taking the integral of this thing and divided by length 3. This is a good time to learn Maple or something else. How did you integrate this back in calc? Had to do it by parts twice and solve the algebra. It was a lot of fun, wasn't it? Good. All right. Does that make sense then? Okay, so you have the initial temperature in there. At equilibrium, that temperature will have spread out based on what's being generated in there. Okay. Other questions on these? Make reasonable sense then? Yes?
Based on when you do the annual water, and so in this case, water you multiply by
By what?
the average.
So the constant in the solution is going to be based on that average temperature across the rod, which is basically what this spreads out to. It spreads out, you get an average there for the temperature that's from the initial one, and then it gets shifted based on this energy being generated there, so you get a quadratic shape to it. But that constant, it has to go above and below that. All right. Other questions on these particular problems? Any questions? Well, hopefully it's not too bad, but yes.
So how do we know that, because isn't there values for beta that aren't for the equilibrium condition? Or is it
Well,
not?
any value other than the one that matches up with the heat.
Okay, I was just kind of confused with the
If
problem.
you just choose an arbitrary beta, if you just flip the coin and decide I want beta to be this, odds are you're not going to be in equilibrium.
Okay, yeah, I was just
There's going to be
confused.
one value that matches what's coming in and what's generated. So this is what's coming in from the left, this is what's generated on the bar, that has to be going out for it to be in equilibrium. And that should make sense to you. What comes in must be what goes out. Otherwise, things are going to rise. Or a lot of people are answering, like the Newton's law of cooling, is that it was temperature going out to the environment. Well, the temperature could be coming in from the environment also, right? We pretty well know that if it's hot outside, the temperature comes in. So you have to worry about whether it's going in or out of that sort of stuff. So that's the flux conditions. And those are related to the Neumann conditions. And the problem we were leaving, and we'll start up with again, is what's happening with the flux conditions. And the only way you get flux conditions being 0 is insulated the partial of u with respect to x equaling 0, no flux, that's insulated, right? There's no exchange of heat, we're being insulated. This This is obviously not insulated because we have heat moving in. But again, using our superposition principle, if I added two solutions, each with flux being 1, then you get a flux equals 2 coming in. That doesn't match, right? You can only work with things if it's homogeneous. But this set of problems is what happens when we have non-homogeneities. We can get that solution. And then coming back to coming back to this one right here, our general solution to this non-homogeneous problem, we can break it up into a homogeneous part and an equilibrium solution. We're solving this part, and then I'm saying the second part of this is, once you subtract out the equilibrium, we're just dealing with the homogeneous problem. That's going to allow us a lot of the mathematics we can work with. But then, all we do to get the total solution is the stuff we're in the process of working on, plus this stuff, which you just now did. And again, this stuff is just an ODE. Everybody agrees that's just an ODE in that case. Other questions on that? Okay, everything's fine with this? All right, so let's go back to where we were last time. All right, so reminder last time, as I said, so the first problem we worked was the nice basic heat equation with the Dirichlet homogeneous on each end. In other words, we're keeping each endpoint at temperature 0. Nice, easy one. And that gave rise to what series? Fourier series with sine. Fourier series can have other ones, as we're going to see. But it was sine series, right? Because the sine function passed through, we got it so it passed through 0 at 0 and L, right? That was the important part of it. So Dirichlet gives rise to sine functions. Now, this is no longer Dirichlet, is it? This is Neumann conditions, because we have the partial of u with respect to x at 0 and L. So we're insulating the two ends on this. Okay. Now, going with your intuition, if I have u of x and 0 being f of x, what should be the steady state temperature of this? Somebody answered it last time. I'm still here. What was going to be the temperature at steady state for this particular problem?
A constant?
It is a constant, but what constant?
Would it be the average
Of
of f of x?
Of f of x. So it's going to be 1 over L, the integral from 0 to L of f of x dx. Okay. So that's what we should get for the average. And that's actually going to also be our first Fourier constant solution. All right. Okay. Any questions on this one? So here's what we're doing. We're doing this Neumann problem. And last time we did the separation of variables. It's the same PDE, so it's the same separation of variables. We get the same separation constant there, the minus lambda. And we just started, and I know I did a fairly accelerated part through it, but I want to remind you, so then that constant there, it could be, we're going to later show it cannot be complex, but it could be negative, it could be 0, and it could be positive, that constant lambda. Now, to have a nice equilibrium, we're hoping because this one, remember, what was the solution to that?
Y equals C.
Okay. So that particular solution, we already came up with that g of t is going to be equal to some constant e to the minus k lambda t, right? And for this to make physical sense, then we better have these be positive constants so that it's a decaying solution. All right? Okay. So, the other problem, of course, we were looking at was the phi double prime plus lambda phi equaling 0, and we have that phi prime of 0 is equal to phi prime at L is equal to 0. Okay, again, so one of the things that's important is you've got to focus in what are the specifics on the boundary conditions. And they're going to make a difference as to what happens. All right, so I think we had already started that if, this is case 1, if lambda equals 0, we're solving phi double prime is equal to 0. And what does that tell us? What's the general solution of phi double prime equals 0?
C1x plus C2.
Okay. It's a nice linear function. Phi of x is equal to a c1x plus a c2. Now we plug in what is phi prime at 0. Okay, so first of all, it has to be 0 because of this condition here. But if we take the derivative, what do we get?
C1.
We get c1. So necessarily c1 equals 0. And what is phi prime at L? It's 0, which is
C1.
also c1. It's a linear function. The slope is c1 everything. Right? And we can see that we have to have that slope being 0. It's a nice constant function, right? So what we have here is the C2 is arbitrary. So that tells us that lambda 0 equals 0 is an eigenvalue, and phi 0 of x, we might as well take it equal to 1, is an eigenfunction. That's it. Everybody agrees that 1 is a non-trivial solution to this particular boundary value problem. There's actually infinitely many because C2 is arbitrary. You get any constant solution is a solution to this one. Yes?
Is it not just sufficient to say that C2 is arbitrary? Because then at that point, it's just like,
Well, what I do want to have is I do want my sets of eigenfunctions and I like to normalize and take, well, it's actually not normalized, but it's fine. But the way you say it, all right, now, yes,
Is this a useful solution?
is this a useful solution?
Yeah. Like, it doesn't seem like it's very useful.
No, it's important, it's essential.
So what? does
It's
it-
essential.
what
This
does
is the
it
one
tell
that the
us?
students most get their points taken off for.
So what
Not
does it-
getting this
yeah,
particular.
What does it tell us about the system? Okay.
Well, what did we already say was a solution of this particular equilibrium problem? What'd you say it was? It was the average temperature of the initial condition.
Right. Is that the average? So you could choose C2 as the.
C2 is going to be that average
Okay,
temperature.
That makes sense.
So my C2, we've already said, intuition tells us it's 1 over L, the integral from 0 to L of f of x dx. And it can only be obtained by that initial condition because that's the heat. Remember, this is an insulated rod, insulated on the boundaries, that heat's trapped. So all it can do is diffuse and flatten out to that constant solution. And that's an important solution. The other ones, because it's going to turn out all the other eigenfunctions we're going to have are going to be orthogonal to this. So if you don't have it, you don't have a complete set of eigenfunctions to get any function we want. Okay, so the case 2 we have. Okay, so the next case we're going to look at lambda is equal to minus alpha squared less than 0. All right? And so we're looking at phi double prime minus alpha squared phi equaling 0, same boundary conditions. Phi prime of 0 equals phi prime at L equals 0. All right, so put a T there. What's the general solution that I have for my phi of x for this particular case?
C1 cosh alpha x plus C2 sinh alpha x.
Okay, we can do that combination. It's best to use Cauchy sinh, and this one seems to work just fine. Oops, where's my alpha? Where's that alpha? All right, and we know that phi prime of x is going to be equal to C1 alpha sinh of alpha x plus C2 alpha cosh of alpha x. All right. And so we look at phi prime of 0. All right. First of all, we do know it's equal to 0. But from this, what do we get? From this line right here? C2 alpha. Now, alpha is non-zero. Okay? So that tells us what?
C2 is equal to
Necessarily C2 equals 0. Now, let's look at phi prime at L. Well, phi prime at L is going to be equal to C1 alpha sinh of alpha L, right? And that has to equal 0. Everybody okay with that? Put that value in there. Now, what does that imply? It tells you that necessarily C1 equals 0 because the sinh is non-zero, positive. The alpha is positive, non-zero. And so necessarily C1 equals 0. So this implies C1 equals 0, trivial solution. So we're not generating any eigenvalues or eigenvectors from that part. Are you okay with that part? Okay, so let's erase this. Case 3. As we already expect, we're not going to get very far if we only have the one eigenfunction. We're going to need more. We better have, and general functions infinitely many, infinite dimensional, so we better have infinitely many of them. So we're going to solve now. Lambda is equal to alpha squared greater than 0. Right? And so the phi double prime plus alpha phi equals 0. All right, so what do we get for our general solution phi of x?
C1 cosine alpha x.
C1 cosine of alpha x plus a C2 sine of alpha x. Let's go ahead and do the derivative. Phi prime of x is going to be equal to minus C1 alpha sine alpha x plus C2 alpha cosine of alpha x. All right. And we look at phi prime at 0. First of all, it's equal to 0 by the boundary condition. From this equation here, what is it equal to? C2 alpha. So that implies C2 is necessarily equal to 0. All right. Now let's look at the other condition. We've got that phi prime at L is going to be equal to minus C1 alpha sine of alpha L. And we want that equal to 0. All right. Now, for non-trivial, okay, we don't want C1 equal to 0. I mean, obviously C1 equals 0 is a solution. That gives us only the trivial one. So the only way we can get non-trivial solutions is what? Then this sine function has to be 0, right? And that sine function is equal to 0 when what's true about alpha? N pi over L. So we're going to have alpha n is equal to n pi over L. Okay? So then that tells us we have eigenvalues, lambda n equaling alpha n squared, which is n squared pi squared over L squared. And the eigenfunctions, what are our eigenfunctions in this case?
Sine of alpha L.
Cosine?
Why is it cosine?
The derivative?
Because it's the
It's not because of the derivative, it's because coming back to the original phi, which was the non-zero constant?
C.
The C1, which is associated with cosine. All right? So then we get our eigenfunction. So this gives us our cosine of n pi x over L. Those are our eigenfunctions. All right? Everybody okay with that? Okay, so all of this is just going through all these different cases we just got through going through. All right, so there's my eigenfunctions. And so now, notice I have a phi 0 and a phi 0 and a phi 1, phi n. And so now we can do our product solutions. So the product solutions U0 of x and t. Well, if I put 0 into that exponential decay for the g and multiply by my phi 0, we'll just get 1. Right? Exponential with a 0 eigenvalue is 1. So we just get 1. And my un of x and t, okay, is going to be equal to, don't put constants in there. I'm going to have this e to the minus n squared pi squared k t over L squared, and then we have the cosine n pi x over L. Alright. So there's my UN. And now we can use a superposition principle, which is gonna say that our U of x and t, so far we've only got finite sums, we can say is the sum, n equals 1 to some capital M of some constant Bn, oops, violated myself. I'm gonna have a B0 from this one, plus the sum n equals 1 to m of b sub n, e to the minus, I'll put the k in front, n squared pi squared t over L squared cosine of n pi x.
Sorry, I didn't see what you were pointing at with the beta, with the B naught, where did that come from again? Oh,
First one. And I like to put it separate because it has a different normalization factor and so forth. So it actually is handled a little bit differently because of the way these functions work. Alright. So there's everybody agrees that this is the G0 times the phi0. This is the Gn with the phi n. Alright? And because of the fact that it's a linear, homogeneous partial differential equation with homogeneous boundary conditions, we can add those up. We can add those solutions up, so any finite sum will work. Now we're going to later show we can take that n going to infinity. Okay, so oops. I'm going to go ahead and put the infinity on this. So superposition principle, if we can let it go to infinity, then we can write it as that. Okay? Then, what do we want to match with this? So I've got my, what's the only condition we haven't handled yet?
The initial condition.
The initial condition. So we haven't handled yet the U of x and 0, which is equal to my f of x. Okay. And so then that should be equal to this b0, often use a zeros, but that's okay, plus the sum n equals 1 to infinity of b sub n. Putting in 0, what happens to that exponential? It just goes to 1, right? And so then we just get the cosine. Do you remember what we did to find those constants?
we observed.
So now what do I have? I have all these, we have this infinite number of constants, right? In front of our eigenfunctions.
Would we
Remember?
do, where we multiply both sides by like cosine and pi?
Okay,
And use that like.
so before I do the cosine, let me first do, let's do the integral from 0 to L of f of x times function 1 dx. Okay, so that's my phi0. And that better be equal to the integral from 0 to L of b0 plus the sum n equals 1 to infinity of b sub n cosine n pi x over L times 1 dx, right? Multiply both by the same, by the eigenfunction, and integrate over the same Okay, so this becomes b0, the integral from 0 to L dx. What does that go to?
L.
That just gives us b0 times L. Now what about this one? Now let's assume we can interchange those. So let's look at the integral from 0 to L of cosine n pi x over L times that 1 dx. And cosine goes to integration. It just goes to, we're going to get L over n pi x sine of n pi x over L evaluated between 0 and L, don't I? Upon differentiation, would those cancel out and we get the cosine?
Just n pi.
Hmm?
Not n- Just an n pi.
Oh, no x there, you're right, no n, no x. Thank you. Now, evaluating at L, what do I get? It's a tough one. You get 0. What happens to 0? Sine 0.
Zero, right.
So that says all of my cosine functions were all orthogonal to that one function. Right? And so that's what I was saying is, if I don't have that function 1, I'm not going to get that average temperature. Because these are all going to shift down to 0. Because the cosine functions go around the 0 axis, right? So you're never going to get it. Okay. I think the next slide helps me with the next part. So then, as you mentioned, what we would like to do is then what happens if we multiply by the m pi x. So we're then going to look at what happens when we look at the integral from 0 to L of f of x cosine of m pi x over L dx. That's going to be equal to, oh, we already showed that the b0 is going to be 0, right? Multiplying by the cosine, that's going to be 0 because it's constant. So then b0, I'm just going to say it goes to 0. And then we're going to get plus, let's go ahead and do the changes. So we're going to have the sum n equals 1 to infinity of b sub n cosine m pi x over L cosine n pi x over L dx. Okay, yes?
Doesn't the B0 go to B0 times L?
I'm saying the b0 times the cosine n pi x integrated from 0 to L, right? Because I'm multiplying both sides by the cosine m pi x.
Okay.
But we already know the integral of cosine m pi x from 0 to L is 0.
Okay, thank you.
So that gets rid of it. That's using that orthogonality we just showed